Hello everyone. Today we're going to be working through a combined loading problem of mechanics of materials. An angled wrench ABC is fixed to the ground at A. The wrench is aligned along the XZ plane as shown in the figure 2A, such that the AB is along the x-axis and BC along the z-axis. Two point forces of the same magnitude P, one in the negative x direction and the other in the positive y direction, are applied at the end C. The segment AB has a circular cross-section of the radius r as shown um, in figure 2B. The length of AB and BC are A and B respectively. Determine the resultant load, aka the forces and moments, on the cross-section at the ground due to the applied forces at C, and determine the state of stress at point M located on the cross-section at the ground. Show the non-zero stresses on the given stress element. Determine the state of stress at point N located on the cross-section at the ground, and show the non-zero stresses on the given stress element. First, what we're going to do is we're going to solve part A. So, uh, oops, kind of going to switch to my drawing tool. So part A will be first drawing a free body diagram. So first what we have to identify is the positive coordinate axes. The positive coordinate axis is defined to be in 3D, y, z, and x. And it's worthy to note that this coordinate system is only defined as positive for the external forces applied on the system. So, for instance, these two P forces will follow this positive convention over here. However, um, when considering internal forces, we have to be careful because the sign conventions for internal reactions and loads are different than considering external loads and forces. For instance, let's review a little bit of theory. So for internal reactions, we define things as positive when they're in tension. And notice that even though this arrow is pointing to the left, in the context of this portion of the beam, it is positive because the that segment of the beam is in tension. And negative will be when the internal reaction is in compression. Um, And this is important when analyzing this whole structure over here. In addition, we have to note that if we cut a beam in half, the positive conventions for moment and shear is given by positive shear is pointing down when looking at the cut beam from the left end, and the positive moment is counterclockwise. But however, for the right beam, this is not really the case because over here we'll have positive shear pointing up and positive moment being clockwise on this end of the beam. So just keep that in mind. So when drawing our free body diagram, we'll first start with um, point B. So this is our origin, and at the origin, there will be reaction forces, and we will define the reaction forces. Um, and the reaction forces are a type of, here we are looking at the internal forces because we are looking at the resultant load, including forces and moments on the cross section at the ground due to the applied forces at C. So the applied forces at C, P and P, are the external forces, while the resultant load is classifying the internal reactions at the point origin. So at the origin, there will be reaction forces in the pos in the x direction, in the z direction, and in the y direction. And notice that although this is kind of like the negative z direction according to our coordinate system for the external forces, it's actually positive when we are considering the internal reactions because these are the directions that define this beam intention. Because note that these forces are all pointing down, and thus the beam is being pulled down, so it's in tension. So these are the forces, so we can define Fz, Fx, and Fy definitely will be some of the reactions. And then we also have moments in each of these directions. We have a moment pointing in the z direction. We have a moment pointing in the x direction. And we have a moment pointing in the y direction. And of course, over here, we have our load P. So there are a few ways you can calculate the force vector. And one of that is by using the sum of forces, and I hat, j hat, and k hat. Another one is simply through observation, which is the method I'm going to use. So notice that according to now looking at our coordinate system for external forces, we have a positive p load and a negative x load over here. So that's the force vector, which is represented by, and let's change the color. Sigma of F is equal to the sum of forces in the x direction, which is simply going to be negative p plus 0 plus nothing because there's no other force in the x direction, comma, our force in the y direction, which is simply positive p, and 0, since we have no force applied in the z direction. Now, what are the units? I think there's no units for this. So now we can look at the sum of moments. Yeah, so now we're gonna look at the sum of moments. The sum of moments is going to be represented also by mx, my, mz. So let's look at the mx direction. So what is going to cause a moment around this direction? And by our right-hand rule, a moment in this direction will be pointing upwards. So it will be our positive mx. So let me see. So P will definitely cause a moment around x at a perpendicular distance of b. But this P force will not cause a moment around x. So the only force causing a moment around x is this P force over here. So thus the moment is equal to mx, which is going to be p. It will be negative p b because this p will cause a moment by the right hand rule pointing down. So it'll be negative pb. Now, what about the my direction? The my direction will be a moment around this axis. So is there any force causing a moment around that axis? Well, if we see there is this P force over here, and this P force will not cause a moment around the y-axis because this p is actually parallel to this y value. So we are only concerned with the p force in the negative x direction, which is this force over here. And by the right-hand rule, it will cause also a moment in the negative y direction. So my will be negative and given by negative p at an r length of a over here. So negative pa. Will there be a moment in the z direction? And the z direction is over here. So yes, there will be a moment in the z direction given by this force over here, but not by this force over here. So this force will cause a rotation in this direction, and the moment will be by the right-hand rule pointing to the right, which is along the positive z direction. So mz will be positive and given by p times the r length of a. So that's pa. And let's check whether we did everything correctly. So mx, we got negative pb, which seems to be, it is correct, okay. My is given by, oh, actually the a is supposed to be b. So let's change that. It'll be pb because we're rotating in this direction and the r length will be this b value. So please double check your answers. And yes, so we have our moment vector now. So we have thus solved for the resultant loads on the cross section at the ground due to the applied forces at C. And now we can move on to part B. So part B and C can kind of be combined into one question. So we're going to do part B and part C together. So in general, when they want you to determine the state of stress at point M located at the cross section at the ground, and at point N, they want you to first come up with a table to organize your thoughts better. So in general, it is advised to write down all the possible forces, even if it is zero at that location. So that's what we're going to do. We have our loading and stress state at M and stress state at D. Oh wait, sorry, at N. So first the loading, there's definitely, since it's a three-dimensional problem, going to be fx, fy, fz, and mx, my, and maybe leave more room down here, my, and mz. And these are going to be equal to some value, which we will find. So first let's identify the type of loading that each of these entails. For instance, f of x is going to be axial because we have a p force pointing down, so it's an axial force. Because it's along the axis of x. So f of x is going to be axial. And what about f of y? Well, f of y is acting parallel to the plane, to the x-plane along this direction. So it's going to cause a shear force since it's acting along the plane. What about f of z? Well, there's no x of z in this diagram, so f of z um is, well, if there was an x of z, what will it cause? It will cause only a shear force. And what about the moment around x? Well, the moment around x um will be causing, well, it'll be twisting this way, so it'll be causing a shear force due to torque. Since you're kind of twisting this beam a little bit, and thus there will be some shear force when you're twisting it at the bottom. So shear. And what about my? Um, my is going to be a bending shear because you're kind of applying it down. So this beam is going to bend this way. And at stress element M and N, they're going to be either under compression or tension. So we have that M of Y is flexural. And MZ is going to be also bending because yeah, MZ is going to be also bending because you're kind of bending the beam this way where it's coming basically out of the plane at you. So MZ is going to be flexural as well. Oops. Flexural. And I guess what they wanted for M of X is not shear, but torsion, which is accurate, but the twisting will cause like a shear over here. So remember that f of x is equal to um, negative p, and the stress theta m is given by the axial stress formula of sigma x equals force over area. And here our force is negative p, so it'll be negative p over the cross-sectional area. The cross-sectional area of this beam, which is equal to of radius r, so equal to pi r squared. And this checks out as when you press down on the beam, it'll be in compression. Um, and thus the negative sign checks out. Okay, now f of y is equal to p. So f of y will cause a shear force. But will it cause a shear force at the stress state of m? We have to ask ourselves that question whenever we consider the stress state. Well, at the point n, where uh, it's oriented like that, so f of y will cause a torsion. Wait, f of y will cause a shear force, yes. But since um m is at the very top, according to our formula for shear force, our general formula for shear force, which is T equals VQ over IT, where Q is A star, Y bar star. Our Y bar star here will be equal to 0. since it's at the very top and there is no area above that stress element location. Um, remember how we calculated the shear stress using this formula over here. So that being given, our shear stress will be equal to 0. So shear force, and it's acting on the x plane, yeah, on the x plane in the y direction. So how xy will be equal to 0 at that location. What about the stress states at n for f of x and f of y? Well, since it's an axial force acts evenly across the face of the stress element. If we draw our stress element, we can clearly see this. There's a side view of our stress element with M over here and N being over here. And our XZ plane is oriented like this. Oh, wait, sorry. This is Z. This is X. So axial force acts evenly across every point. So this the stress element M and the stress at stress element N is going to be equal. So sigma X will be equal to negative P over pi R squared, also at stress element N. And I wanted to show you guys this formula for the shear stress, which is given by the VQ. The VQ equals VA star Y bar star over the moment of inertia around the centroid times the thickness at that point. So this was the formula I was referring to earlier. Um, and for the stress element at N, we're going to have the shear force on the X face in the Y direction is given by the maximum shear stress equation for a circular cross-section. And that is because, as we see over here, the Fy is the P direction and is being applied across the MN face. So if P is going like M is here, N is here, and P is going across the direction, we're going to have the maximum be at point N because shear force increases in magnitude parabolically. So maximum shear stress is going to be at N. And we can also see this because on this stress element over here, um, given that our shear stress equation is given by VQ over IT, where Q is A star uh Y Y bar star. We are at maximum area here, where the area is the area above the stress element location we're considering. And the Y bar star is the distance from the centroid of the semicircular cross-section to the centroid of the whole circle. It's going to be this distance over here. And notice that the thickness is also maximum at the middle. So that is why in a circular cross-section, the maximum shear stress occurs at point N. So in summary, um, we have a large value for A as it's the area of the semicircle. We have a fairly large value for y bar star, and we have the maximum value for T. We have the maximum value for T, and also maximum value for the shear force. Oh wait, yeah. Um, well, I don't know if we have maximum value for the shear force, but we have T is maximized and A is a fairly large value. As we see over here, T max is given by 4V over 3A for a circle. So we're gonna write 4V over 3A, and that is gonna be equal to, what is V equal to? Well, V is equal to simply P, as this P is basically being distributed across the cross section. Wait, not in that direction because it's along Y. So actually in this direction. So that is going to be our shear force. Our shear force is going to be equal to 4P over 3 times pi r squared. And is it going to be positive or negative? Well, we can, okay. Well, to determine whether the shear stress is positive or negative, we have to consider where our shear force is pointing. So our shear force is pointing in the direction of the positive y-axis. And there's no other negative value here. So the shear stress is going to be along the positive y-axis as well, which implies that it's positive 4p over 3 pi r squared. So in the FZ direction, there's no loading, so all of these are going to be 0. Now we can consider the mx, the moment around the x. So the moment around the x is due to, as we see, negative pb. So it's due to this loading over here. And basically this loading is going to cause the figure to spin in this direction. And it's going to cause torsion over here. What about the stress state at M at that location? Well, the stress state at that location, okay, mx is given by negative pb, and the stress state at M is going to be equal to T shear stress along on the x face in the let me see. It's going to be in the z direction. Because if we look at our stress element over here, wait, oops, or our cross section over here, we have M and N over here. And a torsion is going to cause the instantaneous shear stresses at these points to be pointing in this direction because you're going counterclockwise. And thus, At M, it'll be pointing in the Z direction. And so tau xc will be given by the formula for shear for torsion, which is torque times rho over the polar moment of inertia. And the torque will be given by the moment, since there's only one moment over here, which is mx uh, in this direction. And it's going to cause a twisting, and that will be our source of torque. And the rho will be simply the radius of the cross section, which is r. And the polar moment of inertia will be given by the polar moment of inertia for a solid shaft, which we can look up. So we can review a little bit. So our torsional deformation for a solid shaft is given by pi r to the power 4 over 2. So this is the one that we'll be using. So knowing that the polar moment of inertia for a solid shaft is given by that formula, we can substitute now our known values, which is equal to, but the direction for the shear stress over here is actually given by observing the direction of the shear stress on the diagram. So since the shear stress over here has to be pointing to the left, it will be negative. So we add a negative sign here, negative PB. And just note that if you add a negative sign over here already, we're taking the torque to be an absolute value. So we'll take absolute value of negative PB. So negative PB times rho, which is R, as we mentioned earlier, the radius of the cross-sectional area, over pi over 2 R to the power of 4. So this simplifies to negative PB over pi over 2 R to the power of 3, which is equal to um negative 2 PB over pi r cubed. And that will be our final answer for the shear stress on the x phase in the z direction. And for the stress state at n, given by that, it's going to be given by the same torsional formula. Going to be given by at n, it's pointing in the positive y direction, so the shear stress at that point will be positive. It will be tau shear stress acting on the x phase pointing in the y direction, so tau x y, and that will be given by also t rho over the moment of inertia, the polar moment of inertia, and tau will be equal to, as we said before, we cannot simply look at the moment. We have to consider the sign direction of the actual stress state on our face. So since the stress state is pointing down, it will be positive according to our sign convention here. So positive PB times R over, what is it? IP. So the polar moment of inertia again is given by pi over 2 r to the power of 4. And we can simply leave it in this format if we don't want to simplify. It's totally fine. So now we have to consider the flexural stresses. The moment around the y-axis is going to bend the beam this way. Um, and the moment around the y is given by, again, negative PB. And because of this is going to cause a, what is the stress in the actually y direction going to be at M? Well, M is across the neutral axis. As we can see, it lies in the middle. Even here, it lies in the middle. And thus, there is going to be no stress there since sigma y is given by my over I. And the negative means is under compression. So we will look at the diagram to determine whether it's under compression or tension. That's the better method. But basically, over here, wait, sorry. Actually, let's be more explicit. So it'll be my times z. But over here, the z direction, which is the distance from the centroid of the cross-sectional area, is going to be 0. So we can either show that the stress along the y-axis in that direction due to the flexural stress of my is equal to 0 through algebra or equation, or we can just think about it as because the stress element lies along the neutral axis and thus it will be 0 since it won't be either compressed or under tension in that place. As you see, it won't be under tension or compression at that along the neutral axis. Mm. Oh wait, and sorry, actually I meant to say that this is sigma x since I forgot that the x-axis is actually vertical over here, so it will be sigma x equal to my z over I zz. Or wait, actually over here it will be ixx, I believe. Or it's just the moment of inertia around the centroid. So what about the stress element at n? Sigma x will be given by um the same equation, which is m sub y times z over I, but whether it's negative or positive, will be given by observing how the beam bends. So we observe that it bends like this. So the stress element at n will be under compression. So we have to add a negative sign here. So it'll be a negative stress state. If it were over here, it'll be under tension. Since we can see that we are stretching the atoms on by curving it, and we are compressing the atoms by over here, because it's being kind of squeezed together. So the moment around the y-axis will be given by negative PB, but because we decided to add the negative sign afterwards, we have to make sure to take the absolute value of my. Because we are determining the sign using observation of how the beam bends. So negative absolute value of my times, or rather absolute value of my z over I, the whole thing under absolute value. So this one will be equal to um, negative pb over um, times z. So n is located at a distance of r from the centroid of the cross section at a distance of r. So we will take r, and the moment of inertia around the centroid of a circle is given by um pi over 4 r to the power of 4. Um, and how do we know this? We know this from this formula here. It's given by pi r to the power of 4 over 4, as we see over here. Now let's examine the stress data M for the moment around the z-axis. So as observed from our found moment, mz is given by PA, so we can go ahead and plug that in first. And what about the stress state at M? First, we have to consider how the beam is going to bend from this moment around the z-axis. So the moment around the z-axis will be in this direction. So it will cause the beam to bend out of the plane, which from this perspective will look something like this. And we have our stress element at n, m at n at n. Stress state at m. So the moment around the z-axis is going to oh wait, actually is bending towards us, I guess. So we drew this kind of wrong. So let's redraw it. It's going to be bending in this direction. And the stress element M is going to be here and N is going to be here along the neutral axis. Notice that N is along the neutral axis, so we know right away that the stress state along the x-axis is going to be 0 at N. But what about at M? Well, we know that the stress state at X is going to be negative since M will be under compression. Since if we look at it from the XY plane, where should I draw this? Yeah, if we look at it from the XY plane, X and Y, it's going to look something like this. And the point M is going to lie here. So it's actually going to be under compression since it lies, since the beam in this direction is kind of being squeezed. So we know it's going to be negative. And the moment is given by mz, and the distance is uh, given by, the distance is going to be given by uh, y actually, since you're looking at it from this perspective, which is r in the y direction over I. So we know, plugging in known values, we know that mz is going to be equal to PA, and that y is going to be equal to the radius. And we also know that I is the moment of inertia around the centroid of a circular cross-section and is going to be given by pi over 4r to the power of 4. So that is our final answer. So the last and final part is to show the stresses on the given stress element. So on the stress element M, we note that we have stress in the x direction. So axial stress, we note the many instances of sigma x, and we also have shear stress on the x face in the y direction and shear stress on the x face in the z direction. We note that both of the stresses in the axial stresses are negative, so we can simply add them and they'll both be negative. So the stress element will be under compression. Tau xy is tau is shear stress on the x face in the y direction. Um, and actually we don't have that, it's equal to 0. We only have tau on the x face in the z direction, which is pointing to the left since the shear stress is negative. And the z-axis is defined as positive to the right. So using the tail-to-tail method, using the tail-to-tail method and head-to-head method, we can draw the stress element as such, where these arrows are basically tau xz, and this for this stress is sigma x. On the stress element n, we note that we have axial stress in the x direction, and they're also both negative, so we can simply add them to get under compression, which matches our stress element at M for the axial one, which is what we would expect since axial stress is constant everywhere. What about for our shear stress? Well, we have tau xy for both, and both of those are positive. And tau xy is shear stress acting on the x face in the y direction. And since it's positive, it will be pointing outwards. Since we defined the y-axis to be positive, pointing outwards. So it'll be like this. Using the head-to-head method and tail-to-tail method, we can draw our stress element as such. So we have thus completed the problem, and I hope this problem was beneficial to you all. This combined loading problem. See you in the next video.